spatial, with the R position, but also the theta and the phi, the angular side of things, right? So then we can talk about hydrogen atom eigenfunctions, states, with 3 quantum numbers. N for, that would be the eigenvalue of the energy, L for that's the eigenvalue of the allowed angular momentum, and M the z component of the angular momentum, right? So that's the end of chapter 7. Now, I thought it'd be a bit of a waste, given that I've got to send it all off to YouTube anyway, right? All this blank still goes to YouTube with all those extra bits, so I thought I'd use the bits and the space and just show you 4 texts that I'll be using in the future. So 4 courses, 1 text per course. Now this is undergrad level quantum mechanics at senior level, and the next, all in the context of quantum mechanics, more or less. Well, this isn't exactly quantum mechanics, but it's you'll see why in a moment, why I put it here. And I've put it that way because I couldn't get it to stand up. Well, yeah, it did, but vertically it covered stuff, so it wasn't practical. So the next course on quantum mechanics that I'll be teaching, now this is first year masters. This is in fact they're all 3 here M1 level. I put this one at like M1.5. It's between first year and second year masters level. But this will be the next one in quantum mechanics that I'll be teaching by Mandel, and this is also by Mandel. It's not bad. There's a certain overlap with what we've done in the Davies book. In fact, I think either this one's been influenced by Davies or vice versa. I need to check the dates. I think one of them has sort of been strongly influenced by the other. I'm not quite sure who's from which. Now, to do relativistic quantum mechanics, all the Dirac stuff, so the disadvantage with the Schrödinger equation is that it's non-relativistic, right? It can't treat phenomena in quantum mechanics that become relativistic, meaning when the speeds of these quantum particles get close to the speed of light, and then all sorts of weird relativistic phenomena occur, like the mass goes up and that sort of thing. So, so before we move on from just higher level M1 level quantum mechanics treatment to do relativistic quantum mechanics, which is sort of Schrödinger's equation plus special relativity, so you get Dirac's equation, which is fully relativistic. It can handle all the high-speed electrons and whatever. But to be able to understand relativistic quantum mechanics, you need to understand relativity, right? And quantum mechanics, because this topic, which is mostly about Dirac's equation, is a wedding of special relativity and quantum mechanics. So I put in the special relativity book here. It's by French. It's one of the MIT series, quite a famous little book. It's about, I don't know, 200-300 pages, I guess. So we will do a thorough course on special relativity. Do it thoroughly. Understand all the famous phenomena that come out of special relativity. Like time. If you see an observer whizzing past you, you'll see that guy. The guy whizzing past you. You'll see his clock slow down. You'll see his lengths shrink. You'll see his mass go up. All that kind of stuff. Weird stuff. But you need to know this well. So this and this together give you this, right? And then you need to know relativistic quantum mechanics well to be able to move on to quantum field theory. And what's that? Well, it's the quantum mechanics of fields, like electromagnetic fields. And then after this one would be QED, quantum electrodynamics. and after that, because QED is used as a model for QCD, and that would be definitely M2 level, verging PhD 1, first year PhD level. That's QCD, quantum chromodynamics, chromo referring to colour, and colour is a kind of force on the quarks. And QCD is the quantum mechanics of the strong force, the strong interaction, the binding of quarks together by gluons, and well, I won't go much further. Getting way off undergrad level. All right. So if you keep following me, you'll see these books for sure. Let's say I'll be teaching from this one. I don't know, maybe about a year. Now I have about a dozen. So this will be the fourth course, undergrad course that I'll be teaching. I've given myself the task of teaching about a dozen, more or less, undergrad courses as preliminaries, prerequisites to the higher level stuff like this. Because if you don't have it, you can't really teach yourself. You really need those basic prerequisite courses, undergrad, senior level type courses. So I consider that to be fairly important. So in about a year or so, I'll be getting into this stuff, and even this stuff is still relatively elementary compared to string theory and the high level elementary particle physics, and it's still and this is all physics, of course. And that's just half the story. The other half, of course, is pure mathematics. So there'll be a lot of pure math as well. So if you want to become a mathematical physicist, then just keep following me, because I'll be spending as much time on the pure mathematics with pure mathematics texts as on physics. So I look at myself as a mathicist, which is sort of like a mathematical physicist, but because at the highest levels, as I keep saying, pure mathematics and mathematical physics have merged. They've become the same subject, and the seminars on this topic are attended by pure mathematicians and mathematical physicists readily, and they're fertilizing each other and advancing the field together by mastering both fields. They've merged. So pure math and math physics now is pretty much the same subject. And keep following me high enough, you too will acquire that knowledge. You'll be as fluent in the language of pure mathematics as you will be fluent in the language of mathematical physics. So next session will be on a new chapter 8 on particles in a central potential.